Okay, welcome to another fabulous day of Calculus 3. We're going to wrap up section 15.6. The last little piece of it is called differentials and change. So you recall last time what we did is we found that if we looked at the general representation for a function of two variables, that's where we get everything on one side and zero on the other. And then we look at the gradient of that surface. So this is a surface, if you graph it. And if you look at the gradient, which the notation is del big F, X, Y, Z, del is the upside down triangle. This is a vector. It's a vector that contains the first partials of big F. And more importantly, and that's called the gradient, it's a vector that's normal to the surface. It's punching out of the surface, okay? And so that's key for you to know because you use that gradient of big del F to find the equation for a tangent plane and the parametric equations for a normal line to the surface. So that's kind of cool. All right, so what does that have to do with the last piece? We're getting there, but first I want to do a Calculus 1 review for you because we're going to do the Calc 3 analog to the Calculus 1 stuff. So it pays to just do a quick refresher on what your Calculus 1 stuff was. So Math 250, Calc 1. What was the differential? You might not remember, might have been some time ago, but if somebody gives you a function of a single variable, y equals f of x, the differential was f prime of x times dx and is denoted dy. So in other words, you'll see dy is equal to f prime of x times dx. And this is the differential right here. So what? What's it good for? It's good for approximating changes in the actual function f. That's what they use it for. Now, what about the actual change of a function f? Well, the actual change that you can compare the differential with is the function, and it's on this interval, x to x plus delta x. First, you evaluate the function at the rightmost endpoint, f evaluated at x plus delta x, and you subtract from that f of x. And the notation for actual change of y is delta y. And so when you compare these two quantities, they should be pretty close because usually this differential is a pretty good approximation. Now, when is it a terrible approximation? It's terrible if the interval is too large. You want to use the differential on somewhat of a small interval, x to x plus delta x being small. Okay, now the last number 3 here for this definition, your function f is differentiable at a point x equals a, then the linear approximation of y equals f of x at the point x equals a is this equation. Oh my God, what the heck is that? L of x, where L stands for linear approximation function, is equal to the function evaluated at a plus the derivative of a times the quantity x minus a. Now, if you're wondering, like, where the heck did they get that? And I don't remember seeing this in my Calc 1 class. Yeah, you did. Let me remind you real quick. Draw a picture. So back in your Calculus 1 days, you had, say, the graph of y equals f of x, some lovely curve. And somebody might have said, hey, I want you to give me the equation of a tangent line. No, that's not a very straight line, at the point when x is equal to a. And you would do that. You would first get the slope, and the slope was f prime evaluated at a. And then you would use the equation that you learned from an algebra class. This is called the point slope form. You probably remember that from an algebra class back in the day. And this point here has coordinates a, f of a. And so if you're using this to get your equation of your tangent line, then you're going to go y minus the y coordinate of that point, f of a, is equal to the slope, but that's f prime evaluated at a, times parentheses x minus the x coordinate of the point, but that's a. Does anybody remember this, I hope? All right, well, keep going. Now, if you solve this for y by adding f of a to both sides, you'll notice something. Does anybody notice something between this, the equation of the tangent line after I solve it for y, and this thing right here? Can you compare for me? What do you notice?
Pretty much
They're
the
the
same
same?
thing.
Yeah, they're the same. Exactly. And so you can use this equation of the tangent line to approximate the function. And why is that? Because if you stay in a close neighborhood of A, doesn't it look like this straight line is almost the same as the curvy curve of y equals f of x? I mean, if you stay really tight, the straight line almost matches the curve in that little area. And that's why it's pretty good as what we call a linear approximating function. Because as long as you stay real tight around the x equals a, that straight line is pretty good approximation for your curvy function y equals f of x. And that's the point. So let's do a Calc 1 problem, shall we? Let's say you're given y equals f of x, which is x squared. And I hope everybody knows that, you know, that graph is that lovely parabola. There it is. Now, when x goes 1.01, that's a pretty tight interval. What is the differential of y? What's the approximation of the change in y? Well, dy is equal to f prime of x dx. That's the differential right there. There's your differential. dy is equal to f prime of x dx. So dy for us will be 2x dx because the derivative of x squared is 2x. And now the dx is simply the change in x. It's the same as delta x. And so if you're going from 1 to 1.01, then you take the rightmost endpoint and you subtract the leftmost endpoint, and that gives you your dx. Okay? So the dx is going to be 0.01 here, change of x. And the x, you always plug in the starting endpoint, the leftmost endpoint. So the differential of y, when x goes from 1 to 1.01, for us, is that number there, but that's just 0.02. Okay, save that for later. That's the approximate change in your function y. Okay, now what is the actual change in y? Like, how does y really change up for realsies when x starts at 1 and stops at 1.01? So if you use this formula for actual change, so this actual change here, delta y, is going to be f evaluated at the rightmost endpoint minus f evaluated at the leftmost endpoint. That's the actual change. And then what was y? It was x squared. So now we just go, okay, what's 1.01 squared minus 1 squared? Well, that's 1.0201 minus 1. I get 0.0201. That's the actual change. Now what I want you to do is I want you to compare the differential with the actual change. What do you notice? So is our approximate change over here a pretty good approximation? Yes or no?
Yes.
Yes, absolutely it is. And that was the point that you got from Calculus 1 class, I hope. I don't know. Maybe you forgot already. Who knows? Okay. So now they want us to find the linear approximation function of y equals f of x at the point when x equals 1. So folks, you know what they're really asking us to do? That's the same as asking you for the equation of the tangent line. It's the same. Okay, it is the same. So if you just use this handy formula here, you know, y is equal to f of a plus f prime of a times the quantity x minus a, where a is 1, you're going to go y equals, well, f of a is 1 squared, okay, plus, and remember our derivative was 2x, so 2 times 1, and x minus 1. So this is your linear approximating function. Okay, fine. I'm just going to leave it like that. If you want, you can multiply, distribute the 2 and all that other jazz. I'm just going to leave it. And I'm going to replace the y with their notation, L of x. Okay, linear approximation of x. Okay, now what? Well, they want us to now compare, so use it to calculate f at 1.01. So we're going to calculate L evaluated at 1.01. And then we'll compare it to the actual f of 1.01. Okay, so you're going to go just substituting here like that. Okay, this is all to, whoops, come on, baby. Don't leave. All right, and so everywhere there's an x, I'm substituting 1.01. Okay, and then whip out your calculator and then, you know, figure out, do the quick algebra here. And I get 1.02. So that's what my linear approximation function says the value at L 1.01 is. Okay, now what about the actual function at 1.01? We're going to compare that. The actual function is x squared. So what's 1.01 squared? I get 1.021. So now let's compare the tangent line answer basically to the actual function answer. Pretty good, huh? Pretty good approximation. So that linear approximating function is pretty darn good. And that's the whole point from Calc 1. So for letter C here, how does this linear approximation function compare to the equation of the tangent line? Based on what I just was talking about, what would you say?
That's pretty dang good.
Yeah, and
Pretty
they're
cool.
the same. Okay, the linear approximating function they ask for is really basically the equation of the tangent line. That's a good approximation for the actual function. All right, now back to Calc 3. So we're going to do a similar thing in Calc 3. Really? Yeah, for a function of 2 variables. So that's a nice function of 2 variables, and the graph would be some surface in space. Fine. What's the differential of a function of 2 variables? And what are you going to use it for? You're going to, once I give it, we'll write it down in a second, we are going to use it just like we used it in Calc 1 to approximate changes in the function. And then after we get the differential, which is basically what these first 2 things talk about, then we'll look at the linear approximating function for ours, which is going to be, instead of the equation of the tangent line, it's going to be the equation of the tangent plane. And we learned about that last time. So you should know how to do that. All right, here's all these definitions for the Calc 3. So if z is a function of 2 variables, x and y, and delta x and delta y are increments of x and y, then the differentials of the independent variables of x and y are dx is delta x, dy is delta y, and the total differential, which we denote dz, is equal to the partial of z with respect to x times dx, and dx is the same as delta x, the change in x, plus the partial of z with respect to y times dy. That's the total differential for the function of 2 variables. Now, you use this to approximate changes in your function, not the function itself. You use the differential to approximate changes in z equals f of x, y. That's what a differential is used for. Now, the actual change of your function, because you always want to see how good your approximation is. So you'll compare dz to delta z, and they should be pretty close if you stay in a tight neighborhood. This is going to be f evaluated at x plus delta x, y plus delta y. That's the second point they gave, minus the function evaluated at the first point. And that is the change in altitude, essentially, if you're looking at your surface z coordinates. You're basically just evaluating the change in the z coordinates. And hopefully, when you compare these two, they're going to be pretty close. Pretty good approximation. Now, what about the linear approximating function now, which is just the equation of the tangent plane? So if you recall the equation of the tangent plane, let's just do a quick recap. If you have z equals f of x, y, you were supposed to subtract z from both sides. And then all the junk on the right-hand side, you called him big F. And then del big F, the gradient of big F, was looking like this. But what you're going to end up with is, since the only x's and y's that you see are in the little f, big F in this particular case will match little fx. Big Fy will match little fy. And fz, since the only z on the right-hand side is negative z, when you take the derivative of negative z with respect to z, you get -1. And so this is the normal line, excuse me, the normal vector to your tangent plane. So if you have your tangent plane like this, your gradient is punching out like that. That's your normal vector. And so what you do is you use these as once you plug in your point, of course. I'm being very cavalier with the notation. -1, z minus c equals 0. There's your standard form equation. And when you rearrange it and you solve this for z, distribute, move things around, use some algebra, get z on one side and all the rest of the junk on the other. And the z I'm talking about solving for is this guy right here. You'll end up with that. And that's just a rearranged version of the tangent plane, where this is your z. So this is the tangent plane. And he's a pretty good approximation to the actual surface, as long as you stay pretty close to the point that the tangent plane is tangent to. So if I show you a little cheesy drawing here, let's say here in 3D, you have some, let's do like a capping surface, something kind of easy to sketch. Let's say this is your surface. It's basically the graph of z equals f x comma y. I'm going to pick a point right there. There's my point P with coordinates, say A, B, C. And when I draw a tangent plane to that surface, you can imagine this tangent plane to the surface. There it is. And the gradient del big F, evaluated at the point ABC, is the normal vector that's punching out of the surface and the plane. See, that's why we use it when we get our plane equation. So this approximating function is pretty good. I mean, I think you can imagine that this flat plane is almost matching the curve of the surface as long as you stay pretty close to your point. So that's why we can kind of get away with using that tangent plane equation to approximate the actual function, which is, the surface, as long as you stay pretty close to your point. You get too far away, like if I was way over here on the surface, this tangent plane is not so good for that point way over there. I need a different plane equation. Okay? Time to do some examples for Calc 3. So look at this function here, z equals fxy equals 12 minus 4x squared minus 8y squared. Now, anytime I do one of these, and you don't have to do this, it's kind of fun to, as a nice distraction, go and graph it. Like, okay, what does it look like? Who knows? All right, so z, you replace the fxy with z and my software here. 12 minus 4x squared, okay, minus 8y squared. This should be a paraboloid if everything goes well. Whoa! I think I need to zoom out. That thing is huge. Not doing that too well. Wow, that thing is, come on. No. There we go. Okay, so you can see it's a paraboloid, and it's actually, I know there's a lot of spinning that's going on here, but it's actually a downward paraboloid. Nice looking surface though. So if we can work with that guy, and I like to do different colors. Ooh, pretty. How about stripes? Oh, that's nice. How about mauve? Yeah, not so much. How about, oh, that's kind of pretty. Yeah. How about candy stripes? Oh, now that's a good one right there. Okay, we'll go with that. All right. We want to find a linear approximating function. That's just fancy talk for go get the equation of the tangent plane. Okay, that is the same as go get the equation of the tangent plane. Same. Well, how come they don't just say that? Well, you know, I want you to get used to this lingo of using that tangent plane as an approximation function. Okay, so basically that's what they want. So we're going to go through the whole process, and I want you to use this same process when you do a quiz or exam. Step one, get everything on one side and 0 on the other. So step one, I like the general representation. This is the implicit form that we talked about. I want everything on one side and 0 on the other. I don't really care which side everything is on. It's up to you. I don't care, but just get everything on one side. Okay. And yes, then find the gradient. So I'm just going to subtract z, and then I'll have everything on one side and 0 on the other. Yay. And then this stuff on the left is big F. So big F is there. And now step two, you're going to get the gradient. Why? Well, the gradient, you're guaranteed that that gradient of del big F is a normal vector to your surface and hence for your tangent plane. So remember, the gradient is just a nice vector that contains the partials as its components. So del F for us, pretty easy to get here. Let's see, if I differentiate with respect to x, it looks like I'll get negative 8x. With respect to y, negative 16y. And with respect to z, negative 1. So this is a 3D vector that's punching out of that paraboloid that I was showing you. See this paraboloid? There he is. You know, whatever point they're going to pick, what point is one negative 1, 4. So the z coordinate's probably somewhere on there. But let's just I'm just going to pick a point here. That gradient is punching out of the surface at a point. So if I want to create a tangent plane equation, woo, I can easily just use that gradient vector as now they want the I disappeared. Sorry, my internet is unstable.
I thought it was me.
Yeah, I thought that was me too.
Yeah.
No,
I was like, oh no.
it's on my end. I apologize. There's nothing I can do other than, you know, yeah, hold a silent vigil on behalf of Cox Communications and their internet service.
Everybody hates Scots.
So
Not you, Clayton.
yeah, right. So because z is -1 or the z component is -1 in this gradient, it doesn't matter what z value
To
you
your
do.
screen. Stop sharing.
Still, oh, I apologize. I guess
No
when
problem.
I found out, it kills my screen share too. Nice. Thanks for letting me know. Okay. So here's my gradient for this function, big F. Everybody can see that now, right? Okay. So if I evaluate when x is -1 and y is 4, you can easily find the z coordinate, but I'm not going to because it turns out it's f evaluated at negative 1, 4, some z coordinate. When I evaluate my gradient at this point, and the z component is always negative 1, I get the vector what? Positive 8, negative 64, negative 1. Okay. I wish I left myself some more room. So now I'm ready to get the equation of the tangent plane. And so the way I do it is I use the standard form for the equation of the tangent plane. I go 8 times parentheses x minus the x coordinate, but that's a minus 1, plus, and then the next component of my normal vector, that's the gradient, negative 64 times y minus the y coordinate, 4, and then this is the hard part, plus negative 1, z minus the function evaluated at negative 1, 4, and that whole mess equals 0. So I guess we better figure out what our function is evaluated at negative 1, 4. So so this right here, let's do that. What is f evaluated at negative 1, 4? Well, the function was 12 minus 4x squared minus 8y squared. So what is 12 minus 4 minus 8 times 16? Oh, man. Yeah. My brain cannot even think at this time in the morning. 128.
Oh, plus. Okay. Oh, no. So negative. Yeah, and 132, and then
This is
you add
equal
that.
to
That's
minus
negative
120.
120.
Okay, so where does that go? Like, what do I do with a minus 120? Well, that's the z value, the z coordinate of the point on the surface that we're, so I'm going to put a minus 120 right there. Now I'm going to distribute and, try to get this in a prettier form because I want to solve this for z, and then I'll have what I need, okay? So when I distribute the 8 here, I'm going to get 8x plus 8, and then I distribute the minus 64, I get minus 64y. Yeah, I think 64 times 4 is 256. Yeah, and then I get a minus z, and then I get this minus it's a plus, so I have a minus 120 equals 0. There's the equation of the tangent plane. But usually your MyLab math homework will want you to solve for z, and z is what they call big L of xy. That's your linear approximating function. So after I move everything around, folks, and solve it for z and clean it up and make it kind of look pretty, my LXY, my linear approximation function, which is your z, is 8x minus 64y plus 144, okay? So this is my LXY, and what we're going to do right now is use it to do some of the other parts of this problem. So this right here is the answer for part A.
Nope.
Thank you. Thank you very much. So I'm going to use my linear approximating function here, right there, to help me answer part B. And I'm going to estimate F evaluated at negative 1.05, 3.95. Now, after we get the approximation answer, we're going to compare to the actual value and see how good is our approximating function. Anytime you have an approximation, you always want to see how good it is, see if it's worth it. Okay, so we're going to plug in the point's coordinates here, negative 1.05, oof, yuck, and 3.95 into this tangent plane equation. Okay, so we got 8 times the x, all right, minus 64 times that y, 3.95, plus 144. Yucky. Go punch that up in the old calculator, and I get negative 117.2. Save that for later. So that's what the linear approximating function says. Now remember, this linear approximating function is pretty good as long as you stay close to the original value of where the tangent plane was created. And this is pretty close to -1, 4. I mean, when the x coordinate is -1.05, that's pretty close to the -1. And the 3.95 is a y coordinate that's pretty close to the 4. So that makes this okay, acceptable to do. Now, what about the actual function's value at these coordinates? Well, we're just going to substitute those coordinates into the original function up here. That's our paraboloid surface, remember? That's this guy right here. That's the function. Plug it into him. What do you get? I don't know. So now we're going to evaluate f at the point when x is -1.05 and y is 3.95. And you want to keep your calculator handy because who wants to actually do any of the arithmetic for this mess? I get, after I punch it up into the calculator, -117.23. Okay, so now everybody take a look. What do you think when you compare these two? Pretty good approximation? Yes, no?
Yes.
Yeah. They're almost the same, almost. So here's the whole point that you should get, that when you get your tangent plane, you can use it to approximate your actual function as long as you stay close to the point that the tangent plane is tangent to. And it's just like your Calc 1. You can use that tangent line to approximate your function, the curve, as long as you stay pretty close to the point. Same thing. So now letters C and D involve the differential. So now let's turn our attention to, instead of the linear approximating function, let's get the differential only. So what is the differential for this function? Okay, so letter C, they want something else now, not the linear approximating function. Please know the difference, because on the quiz Sunday, I'll give you a function just like here, and I'll have like two parts. One will be answering questions about the differential, and the other part will be the linear approximating function. So the differential dz, let me just write the formula here again, is the partial of z with respect to x times dx, and dx is just the change in x. You just use delta x, plus the partial of z with respect to y times dy, and you can use delta y in place of the dy, okay? So for letter C, they just want us to write out the differential. So first up, here's your function. I'm just going to recreate it here, because now you can go get your partials. dz dx, remember when we were getting a gradient, is -8x, and the partial of z with respect to y was -16y. So the differential is going to look like this: -8x multiplied by dx plus -16y multiplied by dy. And we're done with part C. They didn't ask us to do anything with the differential. They just said, give it. You're like, here you go. I got it just for you. Great. Now what? Well, now let's use it in letter D to approximate a change in Z, a change in the altitude. When XY changes starting from the point -1, 4 and finishes at the point -1.05, 3.95. Okay, and then we'll compare with the actual change. Okay, so but first the differential. So we need to get the dx, and dx is the same as delta x. How does x change? We'll take the finishing value for x, and it looks like x stops at -1.05, minus the starting point for the x coordinate, which is -1. So what is -1.05 minus a -1? I get -0.05, right? So say that. Don't need parentheses around that. Okay, now what about the dy part? Well, dy is the same as delta y, and that's where y stops, and y stops at 3.95 minus the starting point's y coordinate, which is 4. So what is 3.95 minus 4? I think that's also going to be negative, isn't it? Mhm. Negative 0.05. Looks like dx and dy are the same. Does that always happen? No. But we have it here. So now you're ready to use your dz differential. And the x and y are the starting point, x and y. So in place of this x right here, you plug in the starting x coordinate, which is -1. Then you put your dx, which is the same as delta x, and I think we got negative 0.05 here, plus negative 16 times y, that's the beginning point y coordinate, that's 4, and multiply that by the dy, and then whip out the calculator, and I get 2.8. Now remember, this is approximating not the function now, the change in altitude. It's approximating a change. Save that for later. Now we're going to compare that with the actual change of f, the actual change of altitudes. So what is the actual change? Okay, usually they call it like delta z, and it's the function evaluated at the ending point, which is negative 1.01, 3.95, minus the function evaluated at the starting point, which is negative 1.4. Now remember, we already got these two values. We got the f negative 1.4. Remember that was negative 120? Okay, and then this thing, I think we figured it out in one of the previous parts of this problem. Yeah? So did I erase it? Oh, I think it's down here. Here it is, negative 117.23. So you're going to go, all right, negative 117.23 minus 120, right there. And if you do that with your calculator, I get 2.77. Okay, so now is the moment we've been waiting for. You want to compare your differential, your approximate change in altitude, to your actual change in altitude. What do you guys think? Pretty good approximation for that differential? Yes or no?
Yes, very.
Yes, it's a great approximation. Wow, that's amazing. You should all be saying wow for this problem right now. You should all be,
Wow.
wow, thank you. Thank you. You should be duly impressed with this differential. It's pretty cool. And if you're an engineer, you care very much about approximating stuff. Why? Because, you know, you want to model things and you hope that your models are pretty accurate. Same with computer science people. Like if you develop some computer model, you would hope that it's pretty accurate. I just was reading today's news. The Nobel Prize for Physics was split between 3 physicists in the world. And all of them did it for software. What? Physicists do software? And I guess they use machine learning and so on. And they were using these computer software models to model climate and some other changes in the world. Okay. Physics, yeah. So, you know, how good is their model? You know, that's the question, right? So take a look at one really good, cool application for differentials for you engineers and scientists. You can use it to estimate propagated error. This is really important because propagated error happens all the time. How do you, some of you know propagated error? Well, some of you have already ran into it on some of your quizzes and exams. If you round off your answer too early, your decimal answer, you round it to tenths, say weight at the beginning of your problem, and then you use that throughout the rest of your problem, your final answer might be kind of far off the mark because you rounded too early. And that's one example of propagated error. Not good. So let's take a look. Let's say you were measuring the dimensions of a rectangular box. That's pretty easy. You know, just break out some ruler and then measure the box. And let's say the error, because, you know, your measuring tools are never perfect. You should know that. Any measuring tool you use, whatever the measurement, whatever the system, it's always got inaccuracies. Nothing's perfect. Let's say it's off by plus or minus 0.1 millimeter, which isn't bad. That's a pretty good measuring tool. And let's say you measure your box and you get X 50 centimeters, Y 20 centimeters, and Z 15 centimeters. Let's say, that's length, width, and height, say. All right. So using the given measurements, what's the volume of the box? So that's not really anything hard. You're just going to go, well, the volume of the box is X times Y times Z. And I get 50 times 20 times 15 centimeters cubed. And I get 15,000 centimeters cubed. There's the answer to letter A. Okay, now that's what we got from our measuring tool, whether it's whatever it is. But remember, that's a little bit off. That's not accurate because our measuring tool is off by a little bit, not much. But how does that affect how far off we are with the volume consideration? Well, here's the deal. We're going to use a differential to answer this question. Yeah. We're going to use calculus to figure it out. What? You need calculus to figure out propagated error in this problem? You do. So then what? So dV, that's the differential, and I want you to write out the formula. dV dx times dx plus dV dy times dy plus dV dz times dz. Now, right now, it's worth mentioning something. A lot of people may look at this and get confused because this kind of looks like the chain rule, doesn't it? I want to mention something here. This is not the chain rule. And please, if you confuse your differentials with chain rules, even though I know they kind of look the same, because I'm going to show you a chain rule in a second, I will dock you points for bad notation. Yes, indeed, you got to know your notation. So what would the chain rule be if we were using it in this problem, which you're not? The chain rule would involve a rate of change. The chain, let's say the box was, I don't know, remember we had that rectangular block of ice that was melting, and we were trying to find how much the volume was changing per hour, as the box melted. That was a rate. That was dV dt. And that looked like this: dV dx times dx dt plus dV dy times dy dt plus dV dz times dz dt. Does everybody see that this looks sort of kind of like the differential? It does. But what's the big difference between these two so that you avoid confusion in the future? Does anybody see the difference?
It's just dx instead of dx dt.
Yeah, you don't have any DTs going on there. It's not like, oh, you're doing a change of volume per time. So please, this right here that I just wrote out, this is a chain rule formula. And this is not coming into the conversation here. So don't mix and match those two. They're two very different concepts here. So I'm going to go, we don't want to use that for this problem. We want this. Okay. Now, before I use this differential, I want to make sure we stay in the same units, because I don't know if you were semi-awake here, but when they gave the dimensions of the box, they were doing centimeters. And when they gave the dimension of the possible error, they were using millimeters. That's not cool. You want just one unit. So first, let's convert millimeters to centimeters so we're all on the same page. Okay, how do you do that? Anybody familiar with metric? 0.1 millimeter is equal to how many centimeters?
Should we Google it?
You guys are funny. No, that would not be good. 1 centimeter has how many millimeters? Does anybody know?
I think it's 10.
Yeah, I'm pretty sure it's 10 millimeters for 1 centimeter. I'm not a metric expert, but that's the stoichiometry. So then the millimeters cancel, and then what's 0.1 divided by 10?
0.01.
Yes. 0.01. So what are we saying? Our error from our measurement tool, because it's not exactly accurate, would be it's always, whatever length, width, or height that you're measuring, it's plus or minus 0.01 centimeters. So here's the deal. You got your dV. We're going to need to get dV dx. The dx, the dy, and the dz are all plus or minus 0.01 centimeters. All of them. Plus or minus, because that's how far off you are. I got my other guy here. Okay, now what about these partials? We got to go get these. Well, these are pretty easy to get. dV dx, if v is equal to x, y, z, I get yz. dV dy of x, y, z is x, z, and dV dz is x, y. And then you're going to punch in, or substitute in, the x, y, and z that you measured your box, and that was 50, 20, and 15 respectively centimeters. So finishing out this problem, and you definitely, what I do is, since I notice I have a common factor of plus or minus 0.01 centimeters, I am going to factor that out. And then the other factor is going to be my YZ, that's 20 times 15, oops, plus XZ, that would be 50 times 15, plus XY, that was 50 times 20. Whip out the calculator, and then I get plus or minus 20.5 centimeters cubed. So what is this telling us? This is telling us that that original volume answer, 15,000 centimeters cubed, is a little bit off. It could go in either direction. It's 15,000 centimeters cubed plus or minus 20.5 centimeters cubed, because our measuring tool isn't completely accurate. Now, what about relative error? Because a lot of science and engineers have to figure out relative error. Relative error is how far off you are divided by your measurement. So relative error is delta V, I'm blowing my delta here, delta V over V. But delta V is basically our differential, dV. We're going to use our approximation. So for us, it's 20.5 centimeters cubed divided by 15,000 centimeters cubed. The centimeters cubed cancel because relative error has no units. And I get 0.0014. And if I convert that to percent, you guys know how to convert a decimal to percent. Move your decimal place over to the right by 2 spots, and I get 0.14%. So what we're saying? We're saying that the volume that we measured, the 15,000 centimeters cubed, is actually pretty good because it's only off by 0.14%, not even a percent off. So it's pretty good, even though our measuring tool wasn't perfect, because there isn't a perfect measuring tool. It's not bad. And that concludes this section.